Physics change is a fantastically interesting thing. For this, one must study calculus. So calculus is study of change. So calculus can be differential and integral calculus, or combination of both, which is differential equations. So here let's talk about differentiation. So we have already done differentiation in our labs to find out the concentration, let's say, of protein with the OD values from the colorimeter. Sorry, I have just drawn it wrong. Right? I have studied this. Finding the slope of this graph, right? So finding the slope is nothing but differentiation. So differentiation is the slope of the graph, or slope at a particular instant or point. So in physics, if we take a position of particle with respect to time, if we draw a graph of position and time, suppose a particle at t equals to 0 is at x naught, and at t equals to t it's at x. Right, here is the position. It follows a parabolic path and reaches this point at t equals to t3. Here t1, it's t2, it's t3. Here let us consider these 3 points at x equals to 0. We can see that slope would be, right, positive slope, as it's increasing, right? It's positive slope. Here the slope would be 0, as is parallel to x axis, and here the slope would be negative, highly negative. Here the slope is highly positive, here is the slope is highly negative. So this process of finding the slope of at a particular point is called differentiation. So if we draw a graph between so from this, what we get from this graph, right? Sorry, this graph of parabolic part of x and t, slope, what we get slope is the velocity at that particular instance. Here the velocity is positive, here the velocity is 0, and here the velocity is negative. So if we draw a graph between velocity and time, so we draw a graph between velocity, we can write the velocity as dx by dt with respect to time. Here what d represents is small change, which is negligible, right? So dx, if we draw a graph between dx and dt with respect to t, it would be like, first it's positive, it's decreasing, becomes 0, and right, becomes negative. So it would be a straight line decreasing, right? It's a decreasing function. So again, from this graph, right, velocity and time, if we differentiate it again with respect to t, we get this slope as slope equals to v by t, that is acceleration, which is constant. The slope of this graph is constant. That means acceleration versus time graph is also a constant. Now it's not here, as acceleration is negative, speed is constantly decreasing, so it's decelerating. So differentiation of a function can be written as d by dx of function of x. This function f of x can be y, can be expressed as y, or d by dx can be also written as f dash of x or y dash. Again I'm writing d by dx of f of x equals to f dash of x equals to y dash for a function f of x or y. So let's take different values of function. Let's take a function, constant function 3, f of x equals to 3. So d by dx of 3 is 0. That means for any constant, if we take any constant as 3, 4, 5, right, constant c, if we take function as c, its derivative is also 0 as it does not depend on x. For function f of x equals to x, let's draw its graph. F of x equals to x, this is f of x and here is x. Here we get a slope like this. Its slope is a constant which is 1. So here I am writing the functions f of x and here is its derivative, that is f dash of x. So for a constant c, its derivative is 0. For x, its derivative is 1. For constant time that of x, its derivative is c. How? Let's draw the graph to clarify. Here we have this graph for, let's say, 3x. Let's substitute the values. For x equals 0, y is 0. For x equals to 1, y is 3. We get here, right? Oh, so we get this type of graph. For function f of x equals to x, we get this type of graph, but the slope remains the same. That is, the differentiation of cx is so from here we get differentiation of 3x is 3. So what about differentiation of x square? Let's draw the graph. So for x square, the graph would be like this, a parabola, right, whose value is above the x-axis. So here its slope is constantly increasing at both the ends. Here it's increasing, here is again increasing. So if we derive it, we get the value as 2 times that of x. That is, if we draw the graph of derivative of f of x, we get this type of graph. It depends on the value of x. Slope is 2 times. Here again, if we want to find the slope of this graph, again we have to differentiate this. So what about x cube? For x cube, we have this type of graph, function f of x, and time t, we have this type of graph. Here from 0 to infinite, what's happening? It's playing disco. So from 0 to infinite, its graph goes on increasing from here to here. Oh, sorry. It goes on increasing, and again here at the downwards it again goes on increasing. So if we draw the graph of derivative of x cube, what we get is say at positive side of graph, it's increasing, goes on increasing. Again at negative side, it's increasing and goes on increasing for f dash x. For this function fx equals to x cube. So it's the graph what we get for x square function. So from this what we can say is x cube, we get d by dx of x cube as 3x square. So similarly, derivative of 3x square, derivative of x power 4 is 4x cube, and derivative of x power 5 is 5x power 4. So from this we notice a pattern that for a function x power n, its derivative is n times that of x power n minus 1. That's an important function. So let's look at some other functions. Let's see the trigonometric functions. Here in trigonometry, let's take the sine function. Here with time t, here maximum value of sine function is 1, minimum is minus 1, so it would fluctuate like this, right? Value of sine function. If we differentiate this, what we get is, if we differentiate this sine function, let's again redraw this sine function, sine of x as this, we get its differentiation d by dx of sine of x as this. So what this is familiar, it is familiar with function of cos x. So from this we can say derivative of sine x equals to cos of x. Again, if we draw the graph, right, here is the graph of cos x with respect to time, with respect to x, right? So first, I'm drawing that of sine. Here it's 1 initially, it decreases, fluctuates again like this. So if we take the slope of this at each particular point, here it's 0, it's again decreasing, it's highest here, that decreasing, then at this point it's again 0, then it increases, here it's again 0. So if we draw this, slope of this would be like, here it decreases, so it would be from 0, right? Slope is 0, it decreases, then increases, decreases, increases. So if we compare with this with the sine graph is like this. So this derivative graph of cos x is opposite to that of sine x graph. That means derivative of cos x is, so d by dx of cos x is minus sine x. Again, if we take a function which is negative, minus of x, derivative of minus of x is minus 1. Or if we take another tan function, what's the graph of tan function? So graph would be like for 90, 180, 270, 360. Initially it's 0. Yes, initially it's 0, it increases, reaches its peak at infinite. Again from 90 to 180, it goes from negative infinite to 0. Again from 180 to 270, it goes from 0 to infinite, and it continues like this. So if we take the derivative of this, we get here is right here it's increasing function. It's always increasing function. It goes till infinite. So that's actually, if we take the derivative of tan x, we actually get what is d by dx of tan of x equals to secant square of x. So this is some of the trigonometric function, derivative of these trigonometric functions. So derivation or differentiation, what we can conclude is it's an operation of a given function. So if we take this if we take this function, so if we input any value x as 1, we get output as 1 here. If we if we add input of x value as 2, here we get this as 4 for some function of x square. Similarly, for differentiation of a function d by dx of, let's say, some f of x, let's say f of x is x. Here if we differentiate x, we get the output as 1. If we differentiate it with sin x, we get output as cos x. If we differentiate it as tan x, we get secant square x, and so on. So here is the basics of differentiation. So let's do a quick recap. Here in differentiation, what we find is the slope of the graph at a particular instant. So we know that these three types of graph we have talked about is, right, this is for acceleration, it's a constant, velocity is decreasing, and here is the graph, right, this type. So differentiation of the first graph, okay, first would get the velocity. Differentiation of velocity with respect to t will get acceleration. And if we reverse do it, if we take the antiderivative or integration of it, we will integration of acceleration with respect to time, we get this as velocity plus some constant c. This constant c is the initial velocity, and again if we differentiate this, right, here we get this type of graph, x plus some constant again x naught. So these are the basics of differentiation. In integration, let's talk about integration. Here are basic integration we have to for x power n. Integration of x power n is x power n plus 1 by n plus 1. Its integration is, it's reverse of that of differentiation, plus c because a constant term is left over. Differentiation of constant term is 0. Again, for understanding of this, let's again consider the acceleration graph. Here is the acceleration graph. Let's say acceleration is 1 meter per second. So if we take the antiderivative of this, what we can get is a straight line graph whose slope is 1, right? But the graph can be like this also. So the slope of this graph is also the same, it is 1. We can get this one, we can also get this one, we can also get this one. So basically we get a bunch infinite number of lines whose slope is equals to 1. So for this we can say that the, the function of function what we get is y equals to mx plus c, where m is the slope, x is the variable, and c is the constant. It is y-intercept. In this case c equals to 0, but in this case c equals to some negative number, let's say negative 5. So it depends on the parameters